Hi, welcome back to ME 250, lecture 3 today, talking about energy balances. And just to kick things off or to remind you, energy balances apply to control volumes and to control masses. Control volumes, control masses, a way to think about a system. Systems being in the last lecture. And a control volume or a control mass is really just a boundary that contains whatever material you're talking about. And in this course, we're mainly talking about working fluids. Air, water, refrigerant, could be anything, doesn't have to be a fluid, but it is the material being studied. And energy balances apply to fixed amounts of mass, fixed amounts of a mass, which also called a control mass. These are closed systems, closed because the boundary that we draw contains the same identical chunk of mass. In this case, whatever is the mass inside this piston cylinder arrangement. Energy balances also apply to control volumes, also known as open systems. And in this case, we draw the same sort of dotted boundary as the system boundary, but it is an open system in that you could have flow into it and or flow out of it. So it is not a fixed amount of mass, it is not the same chunk of mass, it is a fixed volume. That volume might deform, that volume might move, but it is a fixed volume and things can flow in and out of it. And so energy balances, the first law of thermodynamics, applies to the working fluid or material inside the control mass or the control volume. That's the topic of today. To look ahead a little bit, conservation of energy, energy balances, is the main part of, or the main part of the first half of this course. And then in the second half of the course, we talk about entropy, which is a measure of the quality of the energy, sort of. So energy balances is the amount. Energy can be neither created nor destroyed. It can only change forms. So it's amounts of different types of energy and the transformation from one to the other. Entropy is to do with the quality of that energy. And it's to do with the fact that if you're thinking of trying to get some useful work out of something, you would much rather have several hundred gallons of water up a hill, or a flywheel rotating at some large rate of speed already, or you'd prefer to have several cubic meters of high pressure, high temperature steam. Whereas a much lower quality of energy is the equivalent amount of, say, lukewarm water. There's hopefully some intuitive feeling that one of those, the first three, will give you a whole lot more useful work than the last one. But let's leave aside entropy for now and just think about energy balances. So, one last little bit to remember from our previous lecture is about energy and energy balances, and it's about total energy. So the total amount of energy in a system is going to be expressed as E, measured in joules, and it's going to be made up of kinetic energy and potential energy and internal energy. And as a reminder, we called all of these extensive properties because they scale with the mass of the system. If you have 1 kilogram moving at some speed or at some elevation or at some temperature, and you have 2 kilograms at the same speed, the same temperature, the same elevation, the 1 kilogram has some amount of energy, the 2 kilograms has twice that amount if all other things are equal. What we often work with, therefore, is lowercase, which is an intensive property, which just means that we're dividing everything through by a unit mass. So an intensive property is lowercase e, and if we multiplied that by mass, we would get back the uppercase. And so our kinetic energy is mv squared by 2. Our potential energy is mgz, and our internal energy is specific internal energy, lowercase u multiplied by m. So these are intensive or specific properties. More accurate to call them specific because we've taken an extensive property and divided through by mass. At that point we call it a specific kinetic energy, or a specific gravitational potential energy, or a specific internal energy, or a specific energy. And to do that, let's actually divide through by the mass. So let's cancel out those masses there. And that then leaves us with U, which is specific internal energy. Specific internal energy, or internal energy in general, is it's a property of the material. So it's a property of the material. It's the sum of all the microscopic forms of energy. And we'll expand on that a little bit today. You know what potential energy is, and specific potential energy is just that divided by mass, so it's just gz instead of mgz. But this z is, as a reminder, elevation, obviously, you know that, but it's elevation relative to some reference value. And you know that too, but you maybe haven't thought about it. You always have to pick some reference value to take your mgz from. And likewise, you need to take some reference value for your velocity. So v is velocity. And it's again velocity relative to some reference value. So we're going to deal with total energy in this course. We're going to deal with the idea of conversion from one type of energy to another. We're also going to deal with the idea of getting work out from a change in energy of a system. But first, let's talk a little bit more about internal energy, because internal energy is one of the mostly new concepts in the course, and it's one of the things that people have difficulty wrapping their heads around. So let's talk about it a little bit. So internal energy, it has two main categories. So we can take this thing that we call internal energy, and that we tabulate, and that we look up, and that we calculate, and we can break it up into two chunks. One of them is what we call sensible energy. And this is the portion of the energy, or it's the portion of U, which is associated with the kinetic energy of the molecules. And I should maybe put in the disorganized kinetic energy of the molecules. So it's to do with the translation of the molecules as they move around, bounce off each other. It's to do with the vibration of each molecule. It's vibrating as it moves around. It's to do with the rotation of each molecule. For something like a simple monatomic gas, all they can do is move. They don't vibrate or rotate, or they don't partition energy into those motions. And therefore, the sensible energy is just a measure of its kinetic energy. And here's where you might have already heard of this, because as a result, it's related to temperature. You may have heard correctly that temperature is a measure of the average kinetic energy of the molecules in a gas or a liquid or a solid, and that's true. And so this sensible energy is the energy of those molecular motions, and it's directly related to temperature. So an increase in temperature leads to an increase in U, and a decrease in temperature leads to a decrease in U. Think of an ideal gas, or any gas for that matter. As you pump energy into it, as you increase its temperature, you give all of those molecules more energy. They are moving around more, they're bouncing off each other more, they're vibrating more, they're rotating more, all of those things. As a result, their sensible energy goes up, their temperature goes up, and their internal energy goes up. So the sensible energy is the portion of that internal energy to do with all of those random vibrations and translations of molecules. We're not talking about the fact that on average they're all going from one place to another. That's kinetic energy. We're not talking about that on average they all go from down here to up there. That's gravitational potential energy of the large system. We're talking about the disorganized kinetic energy of the molecules themselves. That holds for gases, that as temperature goes up, the internal energy goes up. It also holds for liquids, it also holds for solids. But if you stop and think about it for a second, something else happens as you add energy, as you add heat to a solid or a liquid. The solid eventually melts into a liquid. The liquid eventually vaporizes into a gas. And that's the second main kind of internal energy that we're going to deal with in this course, which is latent energy, which is the portion of the internal energy U that is associated with phase change of a system, So, for example, to go from liquid to vapor requires energy. And why does it require energy? It's not increasing the temperature, if you remember that from your high school physics or chemistry. If you take sub-zero ice and put it in water, it will raise the temperature of the water to 0, and then until the ice melts, until the phase change is complete, the temperature doesn't increase. So what's happening there, and why does it require energy? Well, it requires energy to break the intermolecular bonds. Intermolecular bonds between atoms. So a solid is a bunch of atoms that are held in some sort of structure, amorphous, crystalline, polymer, doesn't matter, some sort of structure. They have strong intermolecular bonds which are keeping them in that structure. As you add energy, they vibrate a bit more, and eventually they get enough energy to break away and become a liquid where all of the molecules are moving independent of each other. Those molecules in the liquid phase still have intermolecular bonds, but not as strong, and they can move relative to each other. You add more energy to them, they break those bonds and zip off and become a gas with very little intermolecular bonds between each other. So that's the idea of latent energy. It's the energy that is stored in those bonds, and to break those bonds requires energy. if you reform those bonds, you recover energy, and that's phase change. There's also chemical and nuclear bonds, and those are in fact this is another type of potential energy. 2 and 3 would both be termed potential versus sensible energies. We're not dealing with chemical reactions in this course, although if you take combustion in 4th year, there is some in there, and certain other 4th year courses have it as well. We're certainly not dealing with nuclear reactions in this course, although again, if you take energy conversion in 4th year, they'll touch on that a little bit perhaps. But just like with the bonds between molecules that determine whether you're in solid, liquid, or gas, there are bonds between atoms that determine whether it's CO2 or carbon and oxygen. Likewise, there are bonds between subatomic particles that determine whether it's hydrogen or a proton and an electron. And obviously you can break it down farther and farther and farther. All of those are types of energies. In this course, we will just focus on the latent energy of fusion and vaporization, phase change, and the sensible energy, the change in internal energy that is related to temperature. Those are the 2 things we will deal with in this course. But this does bring up a really important point about thermodynamic analysis. In this course, in all of thermodynamics, not just this course, thermodynamics does not provide information about the absolute amount of energy. It only provides information about the relative change in energy of a system. Some examples of this that I'm not going to write down, I'm just going to tell you about them. mgz, the gravitational potential energy, is always referenced to somewhere, right? I'm dropping this from here into my hand, but I could drop it from here onto the ground, or I could open the window and drop it from here onto street level, or down into the sewer, or down to the center of the earth. If we wanted that as a reference, well, can't drop it to there, but I could reference the energy to the center of the Earth. But I could also reference it to the surface of the sun, or the center of the sun, or the galactic center. And yeah, okay, we're getting weird and esoteric and out of hand. But that's the point, is that this pen has gravitational potential energy in comparison to the center of the universe. Obviously, that's not useful to us when all of us are living here on Earth. We can't harness that energy. But understanding that idea that there's always a reference to your energy is really important for thermodynamics. Likewise, this thing has immense kinetic energy right now because, like the Earth, it is spinning very quickly. But so is the Earth, so we can't harness that kinetic energy. So this has 0 kinetic energy with relation to me, and so if I'm trying to harness that energy, I can't harness it right now, because I can't slow it down to a speed of 0 relative to the Earth, for example. Likewise, you've got chemical and nuclear energy. This thing has, there's a battery in it, so there's chemical potential energy in it. It's made up of matter, so there's nuclear energy in it. If I wanted to know the absolute energy of this pen, I would have to compare it down to what? Matter-antimatter combination and complete obliteration? Well, again, unless you're actually dealing with a nuclear reactor, that's not useful. So those are some really esoteric ways to talk about how thermodynamics only considers a relative change in energies as opposed to an absolute amount. But there's a really important one for the use of information in thermodynamics, and that's the idea of your absolute 0 or your reference point. So absolute 0 temperature is the lowest temperature you can achieve, and at that point all molecular motion of normal simple gases stops. So that is a nice hard reference to zero energy for those gases, but that's not actually where we say you have zero energy. So if you go into the tables, and we're going to teach you how to do that in the next couple of weeks, if you go into these tables of internal energy versus temperature versus pressure for different materials, etc., you will find that the internal energy, U, measured as always as kilojoules per kilogram for liquid water, has a 0 point. But it's a little bit weird because liquid water at 0.01 degrees Celsius and a pressure of about 0.62 kilopascals is given to be 0. And that's not to say that the energy there is 0. It's not to say that there's no kinetic energy of the molecules, no motion of the molecules. It's just a reference point. That reference point happens to be the triple point of water. And so it's the point where solid, liquid, and gas water are in thermodynamic equilibrium with each other. And so it's been picked as a reference point. And so is there motion? Oh yes, there's still motion of the molecules. What if we cool it further? Well, if we cool it further, we end up with, on that chart, negative internal energy, which doesn't make a whole lot of sense. It doesn't physically happen, but that's okay. It's just a reference point, and we're talking about changes, not absolute amounts. So yeah, it's a reference point, and all other, sorry, let me write this down. All other internal energy values are referenced to this. Internal energy values are referenced to this, or are differences, therefore, with respect to this 0 reference point. So the moral of this story, well, one of the big things that this means is when you are looking up values to use in a thermodynamic calculation, you have to make sure that you're using an internally consistent set of tables. If one of your tables takes the reference point to be 0.01 degrees Celsius and 620 pascals, and another one takes 100 degrees Celsius, well, you're going to be off by a lot. So you need to have an internally consistent set of tables whenever you're doing thermodynamics. So all thermodynamics is based on changes from one equilibrium state to another. Partially, this is, as I said on the last slide, we don't have an absolute amount of energy, we have a change in energy from one state to another. But it's also based upon the fact that we need, in thermodynamics, to deal with equilibrium states. We need to consider the state at the beginning, the state at the end, and maybe the quasi-equilibrium states that it moves through from one to the other. We're less concerned about the process and more concerned with the endpoints, and that's so that we can have well-defined properties, defined well everywhere in the system, have a single temperature or a single density across the system because the system is internally in an equilibrium state. Let's do an example with this. and introduce the basic idea of conservation of energy and how we use it. So, example here is a spring-loaded piston. So the piston is inside the cylinder in its base state, state 1. The spring is compressed all the way to the left. The piston is pushed all the way to the left, and we've pinned it there. We've stopped it there somehow. And we're considering the gas in the other side of this piston to be the system. Sorry, the gas in the other side of this piston to be the system. This whole piston is adiabatic, or this whole cylinder is adiabatic. We demark this by these dashed lines. And I'm drawing them all the way around the system. So this is the symbolic form that indicates that something is adiabatic. And to remind you, adiabatic means there is no heat in or out of this system. It's very well insulated, or the change that we're talking about is going to happen so quickly that there's no time for heat transfer to occur. And as it says, we're holding the cylinder or the piston in place with a pin, and then we remove it. So here's state 2, where we have removed the pin, and the spring has extended and pushed the cylinder to the right. We're considering as our system, pushed the piston to the right of the cylinder, and we're considering as our system the same chunk of mass, now smaller in volume because it's been compressed. So we've removed the pin, the spring expands, the piston moves, and the gas is compressed. How can we treat this thermodynamically? What can we consider? Well, we certainly need to remember to put this in, that the rest of the system remains adiabatic, because we didn't say anything about removing the insulation from the system between state 1 and state 2. How can we apply this? Well, we have energy being conserved, and we have energy as kinetic potential and internal energy. Well, let's assume that this is a closed system. That's a good assumption. We don't see any inflows or outflows of mass, so this is a control mass closed system. Let's also assume it's a stationary system. And by that, we mean that there is no appreciable change in kinetic energy, there's no appreciable change in potential energy. They're both approximately equal to 0. Now, you may look at this and say, well, we don't know if there's a change in potential energy. And you're right, I haven't drawn a gravity vector, so we don't know if this is moving left to right or from bottom to top. But the amount of change in potential energy of that piston, even if it was vertical, is going to be pretty small compared to the change in internal energies. And regardless, in this question, we're just going to assume that it's 0, say that it's moving horizontally. Likewise, you might say, well, at least to start, we are moving from left to right, so there is some kinetic energy in there. Again, let's just assume that it is small compared to anything else that's going on, and therefore assume that it is 0. So if that's the case, then if we don't have any change in kinetic or potential energy, we can set them equal to 0 at state 1 and keep them equal to 0 at state 2, in which case our energy at state 1 is U1 plus the kinetic energy 1 plus potential energy 1, which we're just going to cancel out. And then at state 2, we have E2, which is U2 plus kinetic energy 2 plus potential energy 2, and we'll just cancel those out. How can we make some progress with this then? Well, let's see. Let's do a first law balance on this. And let's write out the general form of the first law balance. So the most general form of the first law balance is that we've got some energy state at state 1. And, well, most generally we could add work into it. We could do work on it, which would increase its energy. We could extract work from it, which would remove energy from it. We could heat it up, which would increase its, we could heat it up, which would increase its energy. We could cool it down, which would decrease its energy. And once you're done all of these things, you reach E2. This is not actually how I usually form this. I usually write this as E2 minus E1, a delta E. Or if you're talking about a very small amount, you might get down into the differentials. But this is in minus out plus generation equals change. And that is about the most simple way of thinking about thermodynamics and conservation of energy that I know of. Work in and heat in minus work out and heat out plus generation equals change. Well, when we're talking about energy, where did my pen go? When we're talking about energy, we can't, energy cannot be created or destroyed. So there's no such thing as generation of energy. We can just bring it in by work or out. We can bring it in or out by heat, and we can change the energy of the system. And that change in energy of the system would be U2 minus U1 plus KE2 minus, well, plus delta KE plus delta PE, but those we already assumed were negligible in this case because we're not changing kinetic energy or potential energy much. We can further simplify this equation. Are we doing work on the system? Well, yes, that gas is being compressed by the piston being pushed by the spring. So there's a force acting over a distance, force of the spring acting over the displacement of the piston. So that's a work. The force and the displacement are both in the same direction, so it's a positive amount, and they are acting into the system. They're pushing both in toward, or they're both directed into the gas that's inside that cylinder. So that is a work in, yep. So the spring pushes in, and we have work in. Do we have work out? No, there's no work out. There's no force over a distance acting out of this system. So there's nothing out. And likewise, there's no heat transfer at all. The system is adiabatic. And therefore, there's no heat transfer in or out. That insulation around it is keeping it fully insulated with no heat transfer. So let's write this one out and make it a bit easier. And our final system is, or our final equation for this system and its change is E2 minus E out equals W in, which is to say the change in the system's energy is equal to the amount of work that's been applied to that system. And this is thermodynamics. This is thermodynamics all the time. It's not a video of what happened. It's not every single event between the pinned piston in state 1 and the expanded spring in state 2. It's snapshots of the start and of the end, and an assumption that we've passed through some equilibrium states in between, and that we're at equilibrium states at the start and at the end. And a really common use of thermodynamics, a really common question in thermodynamics is, what is the work or what is the heat transfer necessary to go from that state 1 to that state 2? That is thermodynamics in a nutshell. And that is what we're going to be doing again and again and again in this course. We're always going to be asking, what are the states that we're in? And writing out in minus out equals change. Work in, heat in, mass in, work out, heat out, mass out equals change in energy of the system. There is no generation of energy, so we're going to always drop that term. A brief aside, brief aside on this, as I was saying. Something that you will come across a lot in thermodynamics is a sign convention, and I want to talk about it for a second. And that sign convention is this. So aside, many in the field of thermodynamics use a sign convention and that sign convention is that you would have Q in minus work out equals the change in energy from state 1 to 2. And so the idea is that they would say Q is positive in and W is positive out. And you'd have to write it. You would lose marks if you wrote W in. You'd always have to write it as minus a negative out. This is a sign convention that comes from the history of thermodynamics. It comes from the origins of it being how much fuel in as heat to get out how much work out as useful energy. Not in ME250 this term. You can use it if you wish. We won't dock you marks for it, but it's a cause of a lot of confusion for people. A lot of people start thinking, well, is the work in or out? And if it's in, I have to apply it as a negative work out value, and people get confused. My general advice is just pick or guess or read what direction things are in. If you know that you're adding energy to something, that you're heating it up or cooling it down, you know that that is a Q in or a Q out. If you see something that you think is, or if you're compressing it, you're probably bringing work into it. If you're expanding it, work out. Use your intuition. And once you're done the question, if you have solved it and discovered that a value is negative, negative what you were solving, a value that you were solving for comes out as a negative value, that just means your intuition was incorrect, and switch it. If it was an in, switch it for an out. If it was an out, switch it for an in. If the sign convention works for you, use it by all means. We're not going to dock you marks for using it. But we're also certainly not going to dock you marks for not using it, because it's a thing that a lot of people really struggle with, and I generally find that it's a lot easier to just think about in minus out of heat and work equals the change, and that seems to work a whole lot better for a lot of people. Okay, so let's also talk now about conservation of energy and energy balances for control volumes for open systems. We've still got ins and outs, but we need a little bit more than we did before, because a control volume or an open system, the analysis of it has to involve flow. In this course, it's often going to be steady flow and steady state, meaning that we have the same conditions for some long period of time. And I want to draw your attention, we'll write this down in later lectures, but I want to draw your attention now that there's two different types of steadiness. There's steady flow, which means that your inflow and your outflow don't change with respect to time. And there's steady state, which means your system doesn't change with respect to time. And those are two very different things. If you turn on your tap and then let go of it, it's running at a steady flow rate. If you take an empty cup of water and put it under that tap, the flow into the system being your cup, the flow is steady. The system, being what's in the cup, isn't steady. So you can have a non-steady state system, a transient system, with a steady flow into it. And it is as simple as saying, what's the flow of water into my cup? What's the rate of change of liquid in my cup? It's as easy as that, but you can deal with it, and there are times when you have to deal with it in engineering thermodynamics, because there's a lot of filling up of things and emptying of things in engineering and thermodynamics. But regardless, when we're talking about, you can do the same thing with energy, with inflows and outflows, whether they be steady or not, and what's in the system, whether it be steady or not. But regardless, you can still write the same sort of energy flow for control volumes. But to do so, you need to express your energy flow in a fluid stream using the rate form. So in that case, what we deal with is we deal with the rate, which we denote with that dot over top of energy. There it is in its extensive sense. And that's just m dot, the mass flow rate, times E. And it has the units of kilojoules per second, or therefore the units of kilowatts. And so it is a measure of power as opposed to a measure of energy. You need to be able to deal with both in thermodynamics. Again, we'll cycle back to all of this stuff that we're going over in the introduction, but I want to give you an overview to begin with. So this is the mass flow rate. And it is in mass, SI units of kilograms per time, SI units of seconds. Obviously, you can convert to other things if you need to. And that mass flow rate is very often going to be expressed as a density times a volumetric flow rate, which is very often, again, going to be expressed as a cross-sectional area times some average velocity. So this would be your average velocity, and this would be your cross-sectional area. Which multiplied together give you a volumetric flow rate, which multiplied by density gives you a mass flow rate, which multiplied by specific energy gives you the amount of energy that's flowing in. And again, that is just the idea that every hunk of mass that flows into a control volume is going to carry its kinetic energy, it's going to carry its potential energy, and it's going to carry its internal energy. You sum those three things up, you've got E. If you sum those up as specific properties, you've got little case e, You multiply by that by mass flow rate, you get the total amount of energy that's flowing into your system. Can do the same thing for inflows, can do the same thing for outflows, and again, then it's just in minus out plus generation equals storage. It's as simple as that. In this case, rate of in minus rate of out plus rate of generation equals rate of storage. Simple as that. So just like we wrote the energy balance for a closed system, let's now write it in general for an open system. Let's specifically think of an open system with steady flow. In minus out plus generation equals storage. And since we're talking about energy, we can't have generation. You can't create or destroy energy. So in minus out equals storage or change. In, three ways that it can come in: heat, work, mass flow rate. So in is going to be the sum of all of the inlet mass flows that each carry whatever is their internal energy. Another in is going to be whatever heat is flowing in. The last thing in is going to be whatever work is coming in through a compressing piston or a rotating shaft or something like that. So there's our in. Out, well, same thing. It is m dot out, E out, plus Q dot out, plus W dot out. Same thing, different subscripts. And you'll also note that in all of these cases, I've got a dot over m dot, Q, and W. M dot is the mass flow rate in or out. Q dot is the rate of heat transfer in or out. W dot is the rate of work transfer in or out. All of those are going to be in the units of kilowatts or kilojoules per second. Kilowatts of energy, of work energy, is something that you can calculate for a rotating shaft or for a moving piston or whatever. Kilowatts of heat is in fact how you measure the heat from a light bulb or a heater, for example. And m dot is obviously m dot. So that's just in minus out. There is no generation of energy. There is no destruction of energy. So it's just is equal to the change. So that is equal to the rate of change, d by dt, of energy in the control volume. Well, but we said steady state, or we said steady flow. If it also happens to be steady state, this is equal to 0 if steady state. And at that point, well, you can just move one of the brackets to the other side and you get what flows in must flow out. That's something you know, right? Let's consider that for a mixing chamber. So mixing chamber is, as it sounds, just a chamber with 2 or more inlets, a big space in the middle that is designed to promote mixing, and then typically 1 outlet. So we've got 2 inlets here, M1 and M2, and M1 is going to carry with it some energy E1, which is going to be some function of its temperature and pressure. Don't worry about that. We'll come back to how we determine that in future weeks. M2 is going to carry with it some energy E2, which is again some function of its temperature and pressure. And again, we'll come back and explain how we get those in the next couple of weeks. And M.3 is going to be the outlet, and the mass that's flowing out there is going to flow out with some E3, which is again a function of its temperature and pressure. And in addition, if say this mixing chamber is mixing hot gases, the mixing chamber is going to be hot, therefore the mixing chamber is going to lose some heat to the environment as Q dot out. And so we'll look more later at all of this, but we can write out right now the first law balance and also the mass balance for this system. So the first law balance would be m.1 E1 plus m.2 E2 is equal to m.3 E3 plus Q dot out. If you take a look at it, we don't see anything that would cause work to be flowing in and out of this system. We don't have any pumps or shafts or things compressing it or having it expand. So there's not no work going on there. We're assuming that it's a mixing chamber of hot gases, so the system is heating up and losing heat to the environment. There's no other way that heat would be flowing in, though, except through those inlets, and those we've already covered. And so we have no Q in, and we have no work in or out, and we have steady state. There's our system. So let's assume this mixing chamber is steady state, hot gases at steady flow. And in that case, there would be our energy balance. And you can also most definitely write this mass balance. And in that case, it's as simple as m.1 flows in, and m.2 flows in, and m.3 flows out. And if it is steady state and steady flow, those three things better equal each other. So here is our conservation of energy, 1, and here is our conservation of mass, 2. And really commonly in thermodynamics, you're going to be applying both of these equations when you're talking about an open control volume system. So I want to finish off today's lecture with an example. And with this example, I'm also going to jump ahead a little bit. So in the next 3 or 4 weeks, we're going to learn all about material properties. We're going to learn about temperatures and pressures and enthalpies and entropies and internal energies and how they all interrelate to each other, how they change with phase change, or with changes of phase. And that's because a lot of engineering devices, you're going to need to use those sorts of properties. What I want to do today is take it as a given that you can look those up and use them in an energy balance to figure out how a device works. So the device in question is an air compressor. It's basically a turbine acting in reverse. A turbine, you're expanding the fluid out, and in the process it's pushing on turbine blades, which basically look like airfoils. They're applying a torque to a shaft. The shaft turns, and you harvest the energy from that rotating shaft. You use it for something. This is reverse. You apply some work in, and that's what we're trying to find. That work in turns the shaft, which turns the turbine, or turns the compressor blades, the airfoil blades. They in turn compress the fluid. And what you want to get out here is high pressure air for whatever reason. If you've ever pumped up a bicycle tire, you've noticed, or you may have noticed, that the air gets hot. When you compress gases and liquids, they tend to get hotter. As a result, the thing doing the compressing, the compressor, is going to get hot. As a result, it's going to lose heat. And so we've got that here as a Q out to the environment of 16 kilojoules per kilogram. And that might seem like a weird unit there. What that is it's the rate of heat transfer Q divided by the mass flow rate. We're given the mass flow rate of 0.02 kilograms per second. At atmospheric densities, that works out to about 20 liters per second. Well, it's always 20 liters per second. Sorry, blah, blah. For air, it's 20 liters per second. Sorry, long day. So that's the m dot. The q dot comes from heat transfer calculations or direct measurements. You'll learn about those heat transfer calculations in 3B in ME 353. For now, take it as a given. So the question then, this type of question is, what work in do we need from a motor or from, I don't know, whatever source? What work in do we need to give us the P2 that we want and to overcome the losses that the increased temperatures cause? And those losses are captured by the Q out, by the wasted heat out of this system. So it's find W in to get the output and to overcome the loss. Really typical thermodynamics question. So how do we approach it? Well, to begin with, we need to figure out what solution methodology to use. So let's recognize that this is a control volume because it is an open system. Let's draw our system boundary to be the working fluid, the air, that is inside the compressor. And let's further assume that it is a steady state device. It is running at steady state, and that the flow rates in and out are steady as well. So steady state, steady flow. What that means is that our m dot 1 is going to be equal to m dot and is going to be the same as our m dot 2. There's no change in mass flow rate through this device, and there's also no change in energy within this device, within the working fluid of this device over time. So what that means is in equals out. In equals out for mass is just m dot 1 equals m dot 2 equals m dot. But in equals out for energy is something that we can write a little bit differently and is a lot more useful here. So in equals out for energy is that, well, in is m dot coming in, carrying with it the energy of that inflowing fluid. There's also work in. That's what we're trying to find. There is no Q in. The environment is not hot or heating this system up. The environment is cooler, and so the system is cooling down. On the opposite side of the equal sign then, we've got a mass flow rate out that is again carrying some energy with it, some total energy with it. We could consider whether we have a W dot out. We don't, because there's nothing extracting energy from this flow. Quite the opposite, we're putting it in. But there is certainly a Q dot out, because the system is hot, and as a result, it is losing energy to the environment. If we make one last assumption that our change in kinetic energy is equal to our change in potential energy is approximately equal to 0, then what that means is that we can ignore the slight elevation change from the top to the bottom of the compressor and the slight velocity change from the inlet to the outlet of the compressor. Those are perfectly reasonable assumptions. Yes, they both exist. However, if you work out the, if you take some representative values of, say a meter and say a couple of meters per second and run them through, you'll find that those energy changes are minuscule compared to the changes in the flow energy of the fluid as it heats up and compresses. So let's look up that change in energy of that flowing fluid. Here's the part where it's take it as given. 3 to 4 weeks from now, you'll learn how to look these up. But for now, take as given. From the tables in the back of the book, that the flow energy at the inlet at T1 and P1 is 280.13 kilojoules per kilogram. And likewise, we can look up for T2, P2. Remember, once you've got two independent intensive properties, everything is defined. So with T's and P's, we've got everything that we need, at least for something simple like air. We can look it up there at that T2 and P2 and find that it's 400.98 kilojoules per kilogram. And we've got everything we need. We can recast the above equation to be that W dot in, the thing that we're trying to find, is m dot times the change in energies, in flow energies of E1 minus E2. And then W in has to be that much higher to overcome the loss of Q out times m dot. And again, that Q out times m dot is going to be a capital Q, is the heat loss from this system. So we can run through that and find that we get 0.02, the mass flow rate given in the question, times that change in energy, 400.98 minus 280.13 plus 0.02 times our heat loss of 16 kilojoules per kilogram. And if you run those numbers, you'll get 2.42 plus 0.32 kilowatts as the two contributions. And our final answer, therefore, is it takes 2.74 kilowatts of work input to compress this fluid. Couple of comments on this. One, that Q loss, that Q out is a bit low. If you run through and figure out what it equates to a housing temperature of about 23 degrees Celsius. That's pretty darn low. That would have to be either a really well insulated compressor or a really well designed compressor, or it's just a low value. Obviously, if it heats up too much and loses too much heat to the environment, W dot is going to come up higher. Also, that W dot is what the shaft needs to feel. Obviously, depending upon what you're driving it with, you might need a motor that can provide more, because the motor might not be perfectly efficient, and you're obviously going to need even more electricity than that, because the windings in the motor are not going to be 100% efficient, and so they all compound on each other. But that is the work at the shaft that is necessary to take air from P1T1 to P2T2 while overcoming the loss Q out. And so you can run those numbers with different numbers in there to find out how things change. But this is a really typical type of engineering thermodynamics question, and it's always just come back to the idea of understanding how the energies change from one place to another, and understanding the works and heats involved, and just setting up that basic energy balance. That's a really useful technique to use all the way through Thermal 1. So thanks for sticking through the first week of lectures. See you next week, where we're going to be starting off talking more about material properties so that we can understand where all of these energies and enthalpies and pressures and temperatures, how they all interrelate, and how we look them up and how we use them. So come on back next week, and yeah, talk to you later.